Good morning, everyone. I'm Guohan Lui. Here I present ServerSwitch, a programmable and high-performance platform for data center networks. This is a joint work with Chuanxiong Guo and many of my colleagues in Microsoft Research Asia. So recently, there are lots of research and innovations in data center networks. To name a few such designs, there are Portland, DCL, and B-Cube, and CAM-Cube, and VL2. So these new designs reveal various aspects of the current data center networks. They propose new network topology, new routing schemes, new congestion control mechanisms, and develop new network services. Since DCN is a new place to explore, many of these DCN designs depart from current practice. That is to say, they may not use traditional Ethernet and IP packet format, or they may not use internet-based single-pass routing such as OSPF, or they may not use TCP-style congestion control. For example, B-Cube uses self-defined packet header for source routing. Portland performs longest prefix match on destination MAC, and the QCN requires a switch to generate its own explicit congestion notifications. Based on these observations, we need a platform to prototype these DCN designs, as well as many future DCN designs. We have three requirements for our platforms. First, we want a programmable and high-performance packet forwarding. Packet forwarding is a basic service provided by the networks. The forwarding rate is the most important metric to evaluate the data center networks. Current Ethernet switches routers do offer wide-speed packet forwarding for various packet sizes. However, the new DCN designs require a programmable packet engine that beyond the traditional MAC and IP-based forwarding. The DCN designs usually encode network topology information into the server addresses and leverage this topology information for packet forwarding. For example, the Portland encodes the factory topology information into their destination MAC addresses, and they use the longest prefix match on the destination MAC address for packet forwardings. In the future, we expect that more and more DCN designs new architectures and topology will appear. So this calls for a programmable packet forwarding engine for various packet forwarding schemes and formats. The second requirement, we would like our platform to be very easy to develop new routing and signaling protocols in control plane, as well as flow and congestion controls. So this DCN designs beyond the data plan. This DCN designs introduce its own signaling and the protocols in the control planes. So, for example, to support the new addressing schemes, the Portland, the edge switches of the Portland need to intercept the ARP packets and reply with physical MAC addresses for the destination server. And there are other examples, such as adaptive routing in B-Cube and the congestion control in QCN. All these functionalities require the switches to be able to filter and process control plane messages. Third, we would like to support new DCN services by enabling such as reliable multicast and the network caches. This requires our platform to support in-network data processing. Since DCN is owned by a single operator, we expect the technology adoption in this environment will be faster than in the internet. So one of the areas is to introduce intelligence into the network. For example, the CAM-Cube introduced network cache services by doing packet filtering, processing, and caching in the networks. And also, we can introduce switch-assisted reliable multicast in DCN. However, existing networking platforms cannot fully support all these three design requirements. First, the commodity switches are usually black box to us. They provide no program interface. Second, the open flow switches went a step further to provide a program interface for us to directly manage the switches. However, they are mainly focused on control plane functions at present. In open flow architectures, the open flow controller is usually a centralized controller managing tens of hundreds of open flow switches. So it's unclear to us that how the open flow controllers can be used to support the new congestion control mechanisms and the in-network data processing, which requires very low latency and high bandwidth data transfer between the open flow switches and the controller. The software routers are highly programmable. However, their performance are not comparable to the switching ASICs. Besides, the batch processing in their optimization introduce higher latency, which is critical for some functionalities such as congestion control. The FPGA-based systems such as NetFPGA are highly programmable and have high performance. However, they are not commodity devices, and it is still difficult to program them using hardware programming languages such as VHDL. Before we discuss our server switch architecture, let me first give a brief overview of switch technology trends. First, the modern switching chip from the Broadcom, and the Marvell have very high switching capacity. For example, the Broadcom Trident switching chip can switch up to 640 gigabit per second. Second, they support a variety of network protocols, such as Ethernet, IPv4 and 6, and MPLS. Third, they are becoming more and more programmable. All these switching chips have a TCAM table for advanced packet filtering. Basically, this TCAM table allows us to match arbitrary contents in the packet header and then do different actions on the packets, such as packet redirections and mirroring. Second is a commodity server. Recently, the commodity multi-core server provides lots of CPU cycles to do packet processing. As recently demonstrated by route breaks and the packet shaders, a modern Helen server can process up to 40G traffic. Third, the high-speed PCI-E interconnect can provide very high bandwidth and low latency data channel between the CPU and its peripheral devices. For example, the PCI-E Gen 2 with 16 lanes have up to 160 GB per second bandwidth and very low latency, less than 1 microsecond. Luckily, the modern switching chips do have a PCI interface, which allows us to use the PCI-E to interconnect the CPU and the switching chip. Based on these observations, we have three design goals. First, we would like to put a programmable packet forwarding engine in silicon. Given that the switching capacity of modern switching chip is so large, we believe that it's unlikely that in any time soon, the software packet forwarding performance can match that of the switching chip. Further, since the switching chip do have more and more programmabilities, we would like to leverage it for programmable packet forwarding engine. Second, we would like to have low latency software forwarding for both control plane and the congestion control messages. In existing switches and routers, the control plane messages are already processed by their embedded CPU. However, explicit congestion control messages are still implemented in hardware. Since the PCI-E provides very low latency between the CPU and its peripheral devices, we would like to go a step further to letting the CPU to generate and process low latency sensitive messages such as congestion control notifications in QCN and congestion control. Third, we would like to have a software-based in-network packet processing. The rich programmability and the high performance provided by the modern server can be leveraged for us to do in-network packet processing, which require far more complexities than the switching chip can provide. So this is the architecture of our server switch. At the top is a server. At the bottom is our server switch card. On this server switch card, there is a switching chip and multiple NICs chips on this card. When the packets come into external ports, they will be first processed by the switching chip, and the chip will decide whether to send the packet back to the external ports or to the NIC chips, which eventually goes to the server for processing. In this architecture, for most of the packets that requires simple packet forwarding, they will be only touched by this switching chip. For those control plane messages and the in-network processing packets, they will go to the servers for processing. To make our platform very easy to use, we develop software stacks in both kernel and user space. We developed CAPIs for switching chip management. And for the packet processing, if the processing overhead is a concern, we can process the packets within the server switch driver in the kernel. If the packet processing overhead is not a concern, for example, the control plane messages, we can deliver the messages to the user space and writing user applications to process those packets. So next, I will further describe the programmable forwarding engine in modern switching chip and the CAPIs. So this is a packet processing pipeline in the switching chip we used on our server switch card. For packets that you will go to a classifier, the header parsers and the modifiers, and then send out. So usually these blocks can process normal Ethernet and IP and MPS packets. However, the most interesting part of this switching chip is that it has a program parser and the TCAM tables. Basically, the program parser allows you to extract a combination of packet fields in the packet header, as well as some metadata, such as the incoming ports. Then, the user-defined lookup keys can be compared in the TCAM table with the TCAM interest, and then get the next hop. Basically, this line will overwrite the default actions that provided by these lines, and then do packet redirections and mirrorings. In this switching chip, the blue modules are highly programmable. Next, let's see how this chip can support various packet forwarding schemes. There are mainly three widely used packet forwarding schemes: the destination-based forwarding, such as IP and Ethernet; the tag-based forwarding, such as MPS; and the source routing-based forwarding used in BCube. As we can see, our switching chip naturally supports these two types of forwarding schemes, and we have more details in our paper. So next, I will further describe the source route, how we leverage the TCAM for source routing-based forwarding. So for those who may not familiar with the TCAM, here are some basics. Basically, the TCAM compares a key with a set of values simultaneously. For each value, there are two parts, the cared parts and the non-cared parts. The TCAM table will only compare the cared parts with a key. For example, for this TCAM, they will compare the first field and the third field. Moreover, for each of these values, they can set the cared parts and the non-cared parts independently. So for source routing, the source encodes an index and a set of intermediate addresses in the packet headers. And the switches along the path will use the intermediate addresses one by one. So basically, when a packet comes into the switch will first extract the index and then extract the intermediate address based on index and use the intermediate address for table lookup. However, modern switching chips usually do not have such hardware logics for this two-step lookup key extraction. Therefore, we use our TCAM to turn this two-step key lookup matching into one step. Here is how we do. First, we set the index and all the intermediate addresses as a lookup key in the lookup key. Then we set the index and the corresponding intermediate addresses as a character fields and other non-corresponding fields as non-character fields. For example, here we set the index as a character fields. Then for index 1, we set the first intermediate address as a character field. Since the first intermediate address may have multiple values, we enumerate all possible combinations and generate, for example, here are 2 entries for the index 1. Then we do similar things for other indexes and generate the TCAM matching table. When a package comes in, it will match the index and the intermediate address simultaneously and get the output port. Here is another example. In this example, the index is 1 and the first intermediate address is A. So it will match the first entry and get the output port. Currently, we have built switching chip management APIs mainly in 3 categories. We allow user to set up user-defined lookup keys, and then manipulate the forwarding table to compare the user-defined lookup keys with the entries in the TCAM and do certain actions. And for congestion control purposes, we allow user to collect traffic statistics such as traffic volumes and the queue length from the switching chip directly. Here, we provide 3 examples. The first API sets up the user-defined lookup key, the UDLK, for the first 6 bytes in the packet, which is the destination MAC address. Second, we allowed you to set up the TCAM table to compare the first extracted user-defined lookup key with value and mask, which is the first 3 bytes. Then, if the packet is matched, it will be redirected to the third interface. So basically, these 2 APIs shows us how we can perform prefix matching on the destination MAC addresses, which is required by the port length. The third API will read the register, read the output queue length of port 0 directly from the switching chip for congestion control purpose. Our implementation has 2 parts, the hardware part and the software part. For the hardware part, we built a standard PCI-E add-on card which can be plugged into any modern server. On this card, there is a Broadcom switching chip with 8 GE ports and 2 10GE ports. The 4 of the GE ports are connecting to the external ports, and 4 of them connect to 2 Intel NIC chips. Each of the Intel NIC chip has 2 GE ports. The 10 GE ports are used for board-to-board interconnection. In some scenarios, you may want to put multiple of these ServerSwitch cards into one server to form a large non-blocking ServerSwitch fabric with more ports. So we manufactured 80 pieces of these ServerSwitch cards, and the cost is roughly about $400. As for the software, we developed the software stack on Windows Server 2008, and we have 3 kernel drivers: the switching chip driver, the NIC chip drivers, and the ServerSwitch driver. The NIC chip driver are directly obtained, downloaded from the Intel website, and we port the Broadcom SDK to our Windows platform and develop our ServerSwitch API based on this SDK. Next, I will give two examples built on these ServerSwitch platforms. In the first example, we show that we can leverage the ServerSwitch to offload the packet forwarding from CPU to the switching chip for B-Cube. The figure here is a packet header for B-Cube source routing. This is a normal IP header, and this is a private source routing headers. As we have mentioned before, our server CPU, our switching chip can process this source routing. However, since our switching chip doesn't allow us to arbitrarily modify in packet fields, here we need to reinterpret the TTL for the index for the source routes. Our platform is very easy to program. We use less than 200 line of C codes to set up the forwarding tables for source routing, as well as filters for the control plane messages. And this is our experiment. This is a comparison of packet forwarding performance between the switching chip and the software forwarding. In the first experiment, we connect FPGA to our server switch card. In the second experiment, we connect NetFPGA to a 4-core i7 server. In both experiments, we use NetFPGA to generate the 4G traffic and let the server switch card and the i7 server to forward the packets. In both experiments, we vary the packet size from 64 bytes to a full-size Ethernet packet. This figure shows a performance comparison between the two experiments. First, for the forwarding rate, we can see that ServerSwitch can achieve wire speed packet forwarding rate, even for the smallest packet size, which is obviously not the case for the software forwarding. As for the forwarding latency, we can see that for full-size Ethernet packet, the forwarding latency is 15.6 microseconds, which is almost ideal, and which is less than 1/3 of the software forwarding latency. For the second example, we implement QCN, the quantized congestion notifications on our server switch. QCN is a new Ethernet congestion control protocol for lossless Ethernet. It is now an EEE standard. The basic idea of QCN is to let the switch periodically sample the Q length. And once the Q length is large, you send explicitly congestion notification back to the source, and then let the source slow down its rate. Various switching chips are implementing QCN in their switching chip hardware. The reason they implement the QCN in hardware is because they need to get the Q length in a very short latency, so then feed back to the source. Otherwise, the source may not immediately react to the congestions. So on our platform, since CPU and the switching chip are connected via very low latency PCI-E channel, we can use CPU to get the Q length immediately and send back to the source, totally in software. This figure shows how we implement QCN on our platforms. Since our switching chip cannot adaptively sample packets, we let the source to mark the packet adaptively, and once the market packet comes into the switch, it will be mirrored to the CPU, and once the CPU gets the market packet, it will query the Q length immediately and send back to the notification to the source. This is our experiment. We connect a sender and a receiver to our server switch card. The sender sends UDP packets as fast as possible, and we change the packet, change the bandwidth on the link to the receivers to create congestion. So then the sender will adapt to the congestion and slow down its rate. And this is our experiment results. And at first, the bandwidth to the receiver is 1G. At the 22nd, we decrease the bandwidth to 200 megabits per second. And suddenly, we can see there is a Q spike, since the bandwidth suddenly dropped to 200 megabits per second. Then we increase the bandwidth by 200 megabits per second every 20 seconds, and we can see the Q length fluctuate around the equilibrium points. So this experiment demonstrates us that we can implement delay-sensitive mechanisms such as congestion control on our server switch platform, thanks to the low latency between the CPU and the switching chip. We do have some limitations. First, our server switching chip only supports modifications for standard protocols. For example, change the MAC addresses and decrease the IP TTLs and change the MPS labels. Due to these hardware limitations, we need to reinterpret the TTLs in our BQB experiments. Second, for some protocols that requires real packet processing, such as congestion control information calculation in XCP, we need to develop the packets to the CPUs for processing, so which requires a longer latency. So this means our platform XCP and our platform is not suitable for protocols that need real-time packet processing. At present, our server switch card only provides 4G ports. So although it can be directly used for server-centric topologies such as B-cube and the CAM cube, we expect that it's cannot be directly used for topologies which requires a large number of ports. However, we can connect the full server switch card into a 16-port server switch, so it is still a viable platform to prototype this kind of topologies. Our server switch here, we explore the design space of integrating a high-performance but limited programmable switching ASIC with a powerful, fully programmed server. So far, we have seen we achieve our 3 design goals, and we have ongoing efforts our 10G server switch with more ports and speed. Thank you.
Thank you for the great. I'm Sang from KAIST, and I worked for Middlebox company, and I found that many aspects of your work are very similar to internal middleboxes. For example, Big IP, which is a middlebox from F5 networks, has a commodity-based general purpose CPU and a programmable switching chip to support line rate, low complexity functions, and they are with PCI Express and high-speed Ethernet links. So what's your unique point of your research?
So basically, our server switch explores the design space of integrating a switching chip with the CPUs. For example, we have found that we can leverage the low latency of the PCI-E interconnect to perform the latency-sensitive schemes, congestion controls, such as QCN, and to move these functionalities out of the switching chip hardwares to the to software. And we also explore the TCAM in the switching chips to perform various packet to get a programmable packet forwarding engine for various forwarding schemes and the formats. So, and we also explore the design space of doing in-network packet processing with our commodity servers. And we have some experiments in the paper to describe the in-network packet processing.
Anirudh Badam, Princeton. I was wondering if you had any insights into what would the performance be if there is some other device which is actually using the PCI bus, let's say a high-speed storage device which is actually doing a lot of asynchronous DMA to the CPU. I mean, do you expect the PCI bus to be a bottleneck if there is a high-speed storage device which is using the bus?
Pardon, can you I mean, I didn't hear quite clearly.
I was wondering if the PCI bus would be a bottleneck if there was some other device which was actually using the PCI, like a high-speed storage device which does a lot of CPU.
I see. I think that on the server board, the PCI-E on their motherboard, the PCI-E is shared by all the devices. in our scenarios, for example, the server switch, our server switch card, that we do not expect to connect multiple other devices on this server. So the server will use the PCI-E interconnect. So alone, so it will be enough. And besides that, I think the modern CPUs provide up to like 32 or 32 PCI-E lanes, so which is large enough for our applications.
Hi, I'm Chang Kim at Microsoft. So I have two quick questions. So it seems the biggest benefit of this design comes from the fact that you actually use TCAM on the chipset, and then you exposes the API for manipulating that TCAM. So, and the other existing paths like IP and Ethernet manipulation, if you're interested in that, you just directly use the API from the Broadcom or the chipset manufacturer, right? So then why don't you just directly use TCAM chipset to implement this instead of using Broadcom chipset? That's one question. And the other question is, for high port density, like VL2 or Portland topology, you said that you could bundle 4 of your cards to form 16 times 10G, but you had only 2 uplink 10G card. So I'm wondering how you can actually bundle 4 of your cards using only 2 uplinks.
Okay. For the first question, so what kind? What kind of the TCAM chips you refers to? So for our applications, we also need to do packet forwardings and modifications, which is not usually just provided by the TCAM chipset. Yeah, this is a first answer for the first question. As for the second, so in our for our platforms, that the 210G ports are not used for uplinks, but used for board-to-board interconnections. For example, in our scenario, so we do not expect we expose 10G ports externally. So it will have 16 G ports server switch, which can be used for prototype factories.
Okay, sir.